Welcome to the 16th lecture of the course. Today our discussion is on yet another category of energy efficient routers. It is known as side buffered deflection routers. In our last lecture we have seen to make routers more energy efficient, the virtual channels or buffers in the input port are being removed, and we are trying to use a concept called deflection routing, where all the flits are assigned to some ports at the end of the assigned time period. Some of them may be productively assigned and some may be deflecting away from the destination. Let us try to revisit some of the concepts what we have seen on the last day. So, input buffers are eliminated and flits are buffered in pipeline latches and network links. So, whatever buffers that you are having in the input side, these were the buffers, and as buffers are being replaced with deflection routing logic. So, all flits coming through the various directions are being assigned some ports and they are moving out. So, input buffers are removed and it will improve your energy efficiency. Now, we have seen what was the role of buffers. If you have more number of buffers, then the saturation point is stretched. If you do not have buffers, then we are going to saturate early, but you are going to get lot of savings in terms of power and energy dissipation. So, the question is, can we have some buffers? Let us say we will not keep all the buffers in all the ports, some other kind of mechanism, and that is what is known as the concept of side buffering, or it is also known as central buffering. Buffers are not available in the input ports, rather we have buffers will be kept at a central location, and after port allocation we see whether should we employ or use these buffers or not. So, this is the parallel diffraction logic called chipper what we have seen. Chipper has an early inject and eject stage, early ejection, and then whenever there is at least one of the input port is free, we are going to inject, and then you have a faster parallel port allocation unit which is known as permutation deflection network. So, this chipper was a work that is published in High Performance Computer Architecture Conference in 2011 by Chris Fallin and the research group. Let us try to see what are the key performance issues in chipper. First one is link contention. Since there are no buffers to hold the traffic, whenever there is contention, when two packets are looking for the same output port, then it may create one of these a scenario in which one of these packet is deflected away from the destination. So, it is going to get a non-productive port. So, how can that be handled? The concept is known as side buffers. All the flits that are to be deflected may be kept in side buffers. Second one is ejection bottleneck. You can see that in the case of a chipper design, only one flit can be ejected per router per cycle. So, when you have simultaneous arrival of flits that are to be ejected, then it will call to lead to more deflections. The scenario typically happens when in a given clock cycle you have more than one flits to be ejected. So, since you have only one ejection port and that is an early ejection port, so can we slightly improve the bandwidth of ejection, eject up to 2 flits per cycle. And third one is deflection arbitration. So, we are using fast deflection arbiter. So, and they are going to deflect unnecessarily because you have the golden flit concept, and only one packet at any given point of time is being termed as golden, all others are not golden. So, can you bring in one more level of priority? So, a new priority mechanism is being brought, that is called the silver flit. So, on top of the conventional chipper architecture, we are trying to introduce 3 more concepts. The first concept is called, rather than permitting all the flits to go in deflection direction, can you save at least a couple of flits or maybe at least one flit per cycle to be accommodated in a special buffer which is known as side buffer. And the second one is called multiple ejection circuitry, and the third one is called introduction of one more level of priority scheme that is known as the silver flit priority. Now, how to buffer deflected flits? So, consider the diagram wherein you are having the chipper architecture that is there. Let us say there are 2 flits, a red flit and a blue flit. The destinations of red and blue is already been shown. Now, assume that the red flit got deflected in the first arbiter and the blue is going to get. So, in this case since both of them wanted on the same output port, we are not able to satisfy them. So, this is the scenario. You have two flits, there is no flits in the other two ports, and the destination of this blue and red are connected to the same output arbiter. This is called as the output arbiter. But because of the structural connection, only one of them will be permitted to this arbiter and the second one has to be given to the other arbiter. So, this lead to an unnecessary deflection. Let us say the red is coming down here and the blue is going down there, and unnecessarily the red flit is going to be deflected. So, can you get rid of this scenario? So, this is something known as the concept of side buffers. There is a unit that is working after the parallel port allocation unit. Now, consider this scenario. You have the same two flits, the red and blue, that is going to come. The red got deflected out and then you have the blue that is going to get the productive port. So, the blue is moving out. Now, what happens to the red? The red is deflected. Now, what you do? Remove up to one deflected flit per cycle from the output port. So, this red flit which is already there, that is going to be removed into the side buffer. That is what we are going to see. The red flit is going to be entered into side buffer. So, buffer this flit in a small FIFO like structure which is called side buffer. And then the third step is re-inject this flit into the pipeline when a slot is available. So, the flit will come into the pipeline in the next cycle, and followed by that we are going to have this flit that is going to move and that may get a productive port at that point of time. So, this way we are trying to improve upon the performance by reducing the deflection rate. So, the concept of side buffer is at most one flit per cycle is being placed in the side buffer, and these are the flits that did not get the productive output port. So, identify one of the deflected flits, place them in the side buffer and permit them to be re-injected into the router pipeline in the adjacent cycles. Now, let us see how are you going to address the ejection bottleneck, the second problem that is associated with the chipper. So, we have already added the side buffer and this is the re-inject unit from the side buffer. Now, consider that let us say you have two flits, both are to be ejected. So, one is going to be ejected like in the normal channel, the other one there is no other way, it has to go all the way and it gets deflected. So, this can be eliminated by a mechanism by which, let us say if that particular flit can come and get out in ejection only in the subsequent cycles. So, it has to go around the network, come back to the same router and then get itself ejected out. Can you improve upon the scenario? And that is what we are going to see here. We are going to have double ejection bandwidth. Whatever is the ejection unit previously we had, we are going to have one more unit after that. So, the first flit, the blue flit gets ejected through the first eject channel and the red flit get ejected through the second eject channel, and both happens in the same clock cycle. So, you are going to have double ejection bandwidth channel. So, addressing the ejection bottleneck is by dual width ejection. That is the scenario that we are going to work on. Now, the third problem that we see in the conventional chipper router architecture is there is a lack of coordination that cause unnecessary deflection of non-golden flits. So, we have seen that in the case of chipper architecture, flits are being prioritized by giving a golden status. One of the flits, the highly old flits, is being given a status known as golden flit, and the golden flit always gets the productive port. So, if you consider a large NOC setup with multiple routers, only one of the router is going to handle with the golden flit and all the other routers are going to deal with non-golden flits. And regarding the prioritization of non-golden flit, only one flit will be chosen by random. So, in the arbiters that you get, one of the flit is chosen by random and that may get a priority. So, the issue is majority of the routers are handling with non-golden flits. So, there need to be some kind of an improvement that can be done on handling with this non-golden flits. So, consider this case. Let us say you have 4 flits, out of which this green color is the destination for these two flits are looking for this destination and these two flits are looking for the top destination. Now, let us say the red flit is going to win at the arbiters because they all are non-golden flits, that means they are of equal priority, that is what is being mentioned here. Now assume that the red flit is going to win at stage 1. So the red flit will proceed into this arbiter. Automatically the blue has to come down. So the red flit will go straight and the blue flit has to come down. That is what is happening with respect to the first one. Now we see what happens in the next two. In this case, you assume green flit loses at the first stage. So green actually wanted to come straight, that is going to lose, so green is going up. And then the yellow is going to come straight. Now you assume that the red flit is going to lose at the second stage. A green which was a loser in the first stage, when it came to the second stage, it has been winner, because when you compare to red, both green and red are of equal priority. Let us say by random priority, now green is going to get preference over red. So this will naturally result in a scenario where green is being given some pot. Now it so happened that green got the first pot and the red got the second one. So in the case what happens? The green is already deflected and now the red is also getting deflected. And this is being quantified here as an unnecessary deflection, because had red got preference in the second stage also, red would have got its destination. Anyway, green is deflected. Now, how can you improve this kind of a scenario? It is called deflection arbitration. You are adding one more priority level and prioritize one flit to ensure that at least one flit is not deflected in each cycle. That is going to be the mechanism. So the highest priority, it still holds, that is a golden flit packet scheme in the network, and that is chosen based upon a static round robin schedule. One of the flit will be golden and that ensures the correctness of the algorithm. The next highest level is called silver flit. So what you are going to have a pseudo randomly chosen flit in every router. So every router we have one of the flit that is being chosen as silver. So there exists a golden flit in the network and there exists a silver flit in each of the router, and the silver flit we make sure that whenever you have a scenario where none of the flits are golden flits, then the silver flit is always going to have the productive port assignment. So by this we make sure that the silver flit in that router gets a productive port. So three important things. First one, we are going to add up a new priority level. This golden flit status still holds, but there exists only one golden flit in the entire network. So majority of the routers will be dealing with non-golden flits. So when you have the second level, like when you have all the flits non-golden, then you are going to consider one of them as silver flit, and that is the way how you are going to improve the performance. So golden flit, make sure that it is free from live lock. Every flit will become one time golden if they are not getting ejected out. And second one, the silver flit is going to enhance your performance. So how are you going to add up a silver flit? So consider that you are going to make one of the flit as silver flit. The red flit is being considered as silver. So in this scenario, none of the flits are golden. The red flit is being given a higher priority, and that is a local thing. Whenever this flit reaches here, one of the flit is being chosen by random. In this case, the red flit is chosen by random. The red flit is known as the silver flit. Now the red flit wants this as the destination. So the red flit wins at the first stage because it is silver. So the red will go straight, the blue will come down. Let us say the green flit is deflected at the very first stage, just like what we have seen in the previous example. So the green is deflected away, giving way. The yellow is given productive port and the green is going to come out. Now the third stage, since the red flit is silver, it is going to have a highest priority in both the arbiter stages. Both in stage 1 and in stage 2, the silver flit is going to win. So the red flit at the second stage also it is going to get winner, and thereby it makes sure that the red flit is winning. So the idea of silver flit is, in both the stages of the arbiter, the silver flit will get highest priority. Thereby you make sure that the silver flits gets a productive port, it will never be deflected. Now this is called the concept of minimally buffered deflection router. So whenever you have link contention, then the solution is side buffer. Second one, the ejection bottleneck is handled by two ejection stages. Third one, we are going to have a two-level priority scheme by introducing a silver flit concept, and silver flit always get a productive port in the current router. So, the idea of side buffer and dual eject MinBD, that was published by Chris Follin and his colleagues. It was published in the Knox Network on Chip Symposium conference in 2012. So, this is the whole idea of minimally buffered deflection router. So, we can see that it has two stages of eject. It has a silver flit module, it has a side buffer, and to take flit into the side buffer we have one unit which is called a buffer eject unit, and we have one unit which will take care of the redirection of flits into the router pipeline. So, this is the way how the entire MinBD router is going to work. So, on top of the conventional chipper router, there are few more architectural enhancements that are added. Basically, the first one is you are going to have dual ejection unit. Second one is you are having a side buffer and a unit to feed data into side buffer and a unit to take data from the side buffer. And the third one is the silver flit priority mechanism. Now, let us try to see what are the limitations of this MinBD architecture. This is the conventional diagram of MinBD. So, here you have two separate stages of ejection. So, what do you mean by two separate stages of ejection? And that will lead to dual ejection port. What you see on the right side slide is the way how a router is interfaced into a tile. So, dual ejection port means we have two ports to connect from the router and one port to connect from the tile to the router. So, how are we going to draw it? Let us say we have one port through which the injection happens, and we have two ports by which the router is going to give back data into this. So, this is going to increase the bandwidth of ejection, and naturally it is going to be a little more costly and space and power consumption. Second one, the concept of preemption will take care of starvation from the side buffer only. So, we are having a circuit which is taking care of the redirection aspect. So, this redirection aspect is defined as whenever flits are there in the side buffer, waiting in the side buffer, but if all the input channels are busy, then that will lead to starvation. So, this is the process by which one of the flit is being taken and that flit is being added into the side buffer, and this process is known as redirection. So, this preemption process will take care of starvation from the side buffer only. The flits that are waiting in the core buffer, that is newly created flits, their starvation is not addressed. And the last problem with respect to MinBD is silver flit is a strictly local selection. So, a flit that is silver in the current router may get a productive port, but once it reaches the adjacent router, then it may not be a silver. You will not be getting a silver flit there. So, there is no guarantee that a flit which is silver in one router will get the silver status in the adjacent router. So, in the current router it may move closer to destination. In the adjacent router it may not be silver, leading to a deflection, then it may again go back. So, that will lead to kind of a zigzag movement, it cannot guarantee progress. So, these limitations were addressed by the next router in the series, that is known as D-bar deflection based adaptive router. This is also a two-stage router, that stage 1 consisting of hybrid ejection unit, flit preemption unit and dual injection unit. 3 units are there in the stage 1, and stage 2 there is a priority fixer, there is a quadrant routing unit, and as usual our permutation deflection network, which is a parallel port allocation unit, and the buffer ejection unit. So, these are the 2 stages and the various functional units of the new router D-bar. Now, it's stage 1 and stage 2. We will try to see. So, this work was published by our research group. It was published in the DATE 2013 conference. Now, we will try to see what are the functionalities of this. One of the main issue with respect to MinBD was, since it is having dual ejection port, it will take care of multiple flits that are to be ejected. But how many of such kind of scenario we get multiple ejections? So, it was found that roughly only 8% of the cases we get multiple flits to be ejected, and that too at high traffic. So, this proposal is going to talk about a hybrid ejection unit. So, this is the zoomed version of a hybrid ejection unit and a fluid preemption unit. So, these two units, what you see on the left hand side of the pipeline, that is a hybrid ejection unit and the fluid preemption unit, have to be discussed in detail. So, the next slide will show hybrid ejection unit towards your left side and the fluid preemption unit towards your right side. So, the duty of hybrid ejection unit is to analyze whether a fluid is to be ejected or not, whether they are destined to the local core or not. Let us see how the hybrid ejection unit works. Consider the scenario where the color coding tells that the black fluids are the ejection fluids and the red fluids will pass through the router to its neighbors. So, this is been shown with the help of an animation. You can just listen to this animation. When the fluids come to the hybrid ejection unit, the combinational circuit there, the intelligence that is embedded in the hybrid ejection unit will check whether the fluid is to be removed to the local port or not. So, when the fluids will come, it is been removed to the output port. So, the fluids will move out through this port. Now, consider a scenario we get two fluids to be ejected. You can see that there are two fluids coming from the input port, both are to be ejected because of the black color coding. In our convention, this black color indicates they are fluids to be ejected and there are two fluids, they are the red fluids. Now, you can see that one of the fluid will move out through the ejection port and the other fluid get occupied in the buffer pool. This is also known as the side buffer. So, this common buffer pool can also be defined as side buffer. Now, when you have a scenario like this where already you have a fluid which came in the last clock cycle is waiting in the ejection bank of the side buffer, and now in this cycle you are getting one more fluid and let us say this fluid is to be ejected. So, that fluid will go to the ejection bank and the one that was previously there, that will go out through the ejection port. Now, you have one more scenario where you have a fluid that is already there in the ejection port and you get two fluids to be ejected. So, in this case, one of them will move to ejection port and the other one will surely get deflected. So, this will happen, we cannot do anything, and we have found that such a kind of a scenario will happen very rarely, less than 0.025 cases, because in two consecutive cycles we should get fluids that are destined for the ejection core. So, this is how the hybrid ejection unit works. We have only one ejection port, but it could potentially handle two fluid removes on an average to the ports, but with one port we are actually managing it. Now, let us try to understand what is the role of dual injection unit. One of the problem with respect to MinBD design was when the fluid that is there in the side buffer is waiting to enter into the router pipeline, it may suffer from the problem called starvation. So, what is essentially starvation? Starvation happens when you have a fluid, it is waiting in the front of the side buffer to enter into the router pipeline, but all the inputs of the router are carrying valid fluids. So, the input ports are not idle. So, there is no vacancy inside the internal channels in the router. We have seen that one of the main principle for injection in the case of a deflection router is injection is possible only if one of the internal fluid channel is empty. So, starvation occurs when all the fluid channels are busy with fluids coming from the neighbor. So, we have introduced, like in the case of a MinBD, they have introduced a redirection circuit where a fluid is forcefully removed to the side buffer, giving way, that is, which will create a slot in the router's internal channel. But that will take care of starvation only from the side buffer. Starvation of the core buffer was not addressed because core buffer was coming later in the pipeline in the case of a MinBD design. So, in this case, in the case of a D bar, both the side buffer entry as well as the core buffer entry are happening in the same unit, and they are working on an odd even based priority. So, fluids from the side buffer, that is a forward bank, common buffer, the central buffer pool, and from the core buffer, they are going to enter them based upon an odd even priority. So, we can see that in all odd clock cycles, preference is given to the flit from core buffer. You can see that in all odd cycles, can you look at the animations once again? You have one empty slot. Since there is an empty slot, a flit can be injected. So, if it is an odd cycle, flit will be injected from the core buffer. So, the green flit that is there in the core buffer will enter and it will move on. Now, we will try to see what happens in an even cycle. Let us say if it is an even cycle, then the flit from the central buffer pool, that is the blue flit, will occupy the vacancy. So, the blue flit will enter and then it pass. Now, if there are two vacancies, now in this case whether it is an odd cycle or an even cycle, if there are two empty slots, then I can inject from both of the circuits. That is how it is going to work. So, this is called the principle of dual injection unit. Now, there is one problem. Let us say all the four are busy, all the four internal flit channels are busy, then the flits that are waiting in the central buffer pool as well as in the core buffer cannot inject. So, they cannot inject, that is a scenario. This will lead to starvation. But if this scenario is going to continue for multiple clock cycles, then the flits that is waiting in the core buffer as well as in the side buffer is going to face the problem of starvation. And this can be addressed by the unit which is called the flit preemption unit. So, we define two components, one is called re-inject interval, other one is called core inject interval. Re-inject interval is defined as the number of cycles of at most starvation can happen. So, the re-inject interval is equal to 2, that means a flit in the side buffer will wait at most 2 cycles. If for 2 cycles, if it is not getting an entry into the router pipeline, then preemption happens, leading to a way for the starved flits. Similarly, we have something called core inject interval. Core inject interval is a scenario where how long, or it is defined as a threshold for how long a flit in the core buffer will wait to enter into the router pipeline. So, that is all about this, and now we will see about the flit preemption unit. So, what you can see that when a flit is moving and that is going to create starvation. So, next time when the flit is moving, it is been removed and then you are able to get. So, in this scenario, in the second scenario, we can see that we have 4 flits that is coming, since the channel is busy and the flits that is waiting in the central buffer pool is starving. So, one of the flit will enter into the router pipeline, whereas the other is going to be removed. So, this flit is going to be preempted. So, that flit is going to be preempted out into the central buffer pool in the next cycle. That is what we are going to see, that the flit is been removed and the red one will enter and they are going to work like that. Now, the next one we will see about the stage 2 of the D-bar pipeline. So, in the stage 2 we have a priority fixing unit, a quadrant routing unit plus buffer eject unit and permutation deflection network. So, first we try to understand what is a priority fixing unit. So, in the case of a chipper, the priority was based upon age, we call it as a golden packet. In the case of MinBD, one more level of priority was introduced. So, we have a golden packet as well as a silver flit. Silver flit selection was completely random. So, a flit that is becoming silver in one router may not become silver in the adjacent router. This leads to a scenario that a flit will move closer to destination in one router, and due to adverse priority mechanism, it may move away from the destination, leading to a zigzag movement, or it is just experiencing some kind of a live lock. So, a new kind of priority mechanism is introduced. The heart of the priority mechanism is when a flit has almost reached close to destination, let us give a priority to it in such a way that it is not deflecting away. So, this can be implemented by looking into the hops to destination. Every flit that is reaching the router, they are being graded or compartmentalized or partitioned based upon the hops to destination. So, the hops to destination D is computed and encoded in 3 different cases. So, consider that you are working on an 8 by 8 mesh NOC where you have 64 routers, and each router is been given a naming X and Y. So, consider the case you are talking about a router 3, third column and third row in the network. Now consider there are 4 flits. What is marked on the flit is the destination number. So the first flit wanted to go to 47, second one wanted to go to 44, third one wanted to go for 03, and the fourth one wanted to go to 11. So these 4 flits are going to reach a router whose coordinate is 33. So the hops to destination is computed by Euclidean distance. So 4, 7, there exists one difference. So from 33 to reach 4, 7, you have to move one hop in the x dimension and 4 hops in the y dimension. So totally it is 5 hops. Similarly 4, 4 will have total of 1 plus 1, 2 hops to make. 03 has to make 3 more hops. 11 has to make 4 more hops. So based upon the number of hops to destination, your flit is being given a priority value into one among these 3 cases. If the number of hops is less than or equal to 2, the priority is given as 0, 0. If the number of hops is greater than 2 but less than or equal to 4, the priority is given as 0, 1. If it is larger than 4, the priority is given as 1, 0. So for every incoming flit, we are going to look at what is the priority value, and this priority value is being used as the key in order to give preference in PDN. So you have 4 flits that is coming. These 4 flits, upon passing through the router, you are going to find out the number of hops. So what you see here is the number of hops, and upon referring into the table, these flits are categorized as category C, A, B and all. So case A is the highest priority, case B is the medium priority, and case C is the lowest priority. So whenever the flits are coming into the priority fixing unit, from the destination address that is stored on the flit, the flit's number, the destination number is extracted and hops to destination is computed, and a priority value, a 2-bit priority value is assigned to them. The next concept is known as quadrant routing and marking. So we have one more unit which is called QRU, quadrant routing unit. So the idea of quadrant routing unit is we will find out a vector, a direction for a flit, and that direction has been assigned with a code, and this binary code will tell which are the possible directions which will take the flit closer to destination and which are the possible direction which will take the flit away from the destination. So consider the left hand side what it is been given. Let us say this is the current router, that is the center of the diagram. Let us say the packet is here. The destination can be in any of these 8 possible cases. It can be in the east north side of the current router. It can be strictly on the north side of the current router. So strictly on the north side means the destination is exactly on the same column as that of the current router. It can be strictly on the south side, that also destination is exactly on the same column but it is towards the south direction. Destination can be strictly on the east or west side, in that case they are in the same row. So we have 8 different possibilities for an incoming packet. So let us say in the current router you got a packet. The packet will belong to 8 of these quadrants. It can be east, east north, north, northwest, west, then southwest, south, and then in southeast. These are the directions, the potential directions that are shown here. So based upon the relative position of the destination router with respect to current router, a 3-bit output vector is generated. So what this 3-bit that you see is the output vector, and this routing is known as quadrant routing. So the output vector is generated. Now there is a marking logic. This output vector is being given to the permutation deflection network, and this PDN is going to have a table structure inside that, and from the table a lookup is made. So PDN can assign one of the 4 ports, that is east, north, west and south. These are the 4 possible ports that a flit can get by passing through the permutation deflection network. Now what you see here is the output vector of a flit. if the output vector is 0, 0, 0 and the port that the PDN gave is also 0, 0, 0, then the marking is 0. That means the flit is in the productive direction. I will take one more case. If the output vector is 0, 0, 1, output vector is 0, 0, 1 means the flit is relatively in east-north direction with respect to current router. Let us say if east is the port allocated. So, a flit got east direction, the destination is at relatively east-north direction with respect to current router, the flit is in the productive path, because east-north, a flit which got east output port is still travelling in the east-north quadrant. That is why we can see that marking bit is 0 means the flit is in the productive port. Now, the third scenario, let us assume a flit's output vector is 0, 1, 0. 0, 1, 0 means this is the output vector. When a flit's output vector is 0, 1, 0, that means destination is exactly in the north of the flit. Now, the PDN is allocating 0, 0, 0. So, when the output port assigned to a flit is east, but its quadrant vector is 0, 1, 0, that means it needed exactly north. 0, 1, 0 means exactly north is what I am looking for, but what I got is east. So, in that case the flit is not in productive direction. That is why it is marked as 1. So, any 1 in this table indicates, or there are many 1s, you can just find it out from this table what are all the different combinations by which you get 1 and 0s. So, any 1 that you get, then that means that the flit is going in a non-productive direction. So, this will in turn help the next unit to take up a good decision. So, the idea of marking is basically to tag a flit, whether it is marked or non-marked. Marked means, if the flit is marked means it is going in a non-productive direction. So, it is a potential candidate to be side buffered. So, the quadrant routing and marking together will help the buffer eject unit to take up a call. So, quadrant vector is nothing but it is a 3-bit value that indicates what is the relative position of the destination with respect to the current router. The destination can be either on the axis, exactly on the east, west, north or south, or it can be in a quadrant where there are 2 possible productive ports to reach that router. And based upon the output vector and the output that is allocated, there is a marking scheme where 1 indicates the flit is marked with 1, that means the flit is not productively assigned, it is deflecting away. If it is marked with 0 means nothing should be done, even though the flit is going in some direction, it is still one hop closer to the destination. Now, let us consider the last unit, that is buffer eject unit. Now, in this buffer eject unit, the PDN's output is going to the buffer eject unit, which is in turn connected to the common buffer pool. The PDN is going to perform marking that we have seen just previously. If the marking is there, then the buffer eject unit's job is easy, the flit is removed to the destination. So, the marking bit is 0, the flit will directly pass through. If the marking bit is 1, the flit is being taken to the common buffer pool. That is the way how the whole idea of buffer eject unit will work. So, that completes the various stages of the D-bar. It had a hybrid ejection unit which will take care of 2 ejections without having 2 ejection ports. You have a flit preemption unit that takes care of the starvation of both side buffer and the core buffer, and then we have a dual injection unit where flits can enter from both the side buffer and core buffer with odd even priority based mechanism. And then you have a priority mechanism which is not working based upon random type silver or golden based on age. Priority is strictly based on hops to destination. Whichever flit is nearing the destination, they may get highest priority. So, you may initially deflect when you are away from destination. As you become closer to the destination, your priority is going to improve. And then you have a quadrant routing unit which will tell you what are the productive directions, and a PDN as usual followed by a buffer eject unit. So, the dual ejection support without 2 stages of ejection. Still we can manage 2 ejection with the help of a side buffer, and to ensure fairness in the progress of flits from the central buffer pool and the core buffer. So, since we are having a dual injection unit that will take care of progress of flits from both side buffer as well as the core buffer, and then the priority computation and the output vector computation. So, these two things are happening parallelly. Since these two things happen parallelly, it is going to save little bit of time, and PDN port allocation is done with the help of a flit marking scheme, and that is going to help this overall port allocation. One more salient feature of D-bar was, when you consider a mesh NOC, the central routers typically carry more traffic, whereas the edge and corner routers are going to carry less amount of traffic. So, the number of flits buffer space in the so-called side buffer, whatever side buffer that you see here, it is typically defined as 4 flit buffer space in the case of MinBD. In the D-bar, they are using a non-uniform side buffer allocation. The central routers are having 4 flit side buffer, the edges are having 3 flit side buffer, and the corners are having 2 flit side buffer. That also is going to save little bit of your space and energy budget. Now, let us try to see the performance comparison. There are two important parameters that is being used here. One is average packet latency, other one is deflection rate, and these are being taken from a simulator, open source simulator known as BookSim. So, there are various synthetic traffic patterns which has been defined in the graph. It's uniform traffic, transpose traffic, and bit complement traffic. These are all artificially traffic generation models where certain nodes are going to create packet to certain other nodes. What you see on all these graphs is, on the x-axis it is called packet injection rate. So, if a packet injection rate is equal to 1, that means that every cycle, every router is injecting a new packet. So, if packet injection rate is equal to 0.5, then at every cycle only 50% of the routers are going to inject packets, or a router is going to inject packet once in 2 cycles. So, across various traffic you can see that the packet injection rate is increasing. As the packet injection rate is increasing, you can see the graph, the y-axis is the average packet latency. How much is the approximate number of cycles a packet is going to take in the network. So, the packets are generated in the network, they are going to travel through the network, and how much time approximately a packet will take. So, it is typically known as load versus latency graph or injection rate versus latency graph. Now, little bit of the result analysis that is been given here. It is a comparison between different techniques. You take this first graph on the left side, this red color is called MinBD. So, as the load increases, the latency of packets which are using MinBD traffic is on the increasing trend. So, latency increases to high value somewhere around this point. And the blue one is a normal input buffered router. Input buffered router, even if you increase the load, still it is low and it goes to high latency roughly around this stage. And the black one is D-bar routers. So, D-bar can accommodate more number of packets in the network. Still it is not saturating. So, this is something like a load latency graph we have seen. If you have less number of buffers, if there is more deflection, then it will saturate early. That is what you can see in the MinBD. So, the trend is there, MinBD saturates early in transpose as well as bit complement traffic, and we can see that this D-bar, that is the black one, is showing slightly better performance in the other two traffic. Yet another parameter that is to be used for analysis of deflection routers is a deflection rate. So, when a flit is not getting productive port, the flit gets deflected away. It is going to other unwanted ports. So, that will increase the number of hops of the flit. So, the more number of hops it travel, latency of the flit is also going to increase. So, this is a comparison of deflection rate of MinBD and D-bar. MinBD, you can tell that average deflections per flit is on the higher side. When it reaches 0.24 packet injection rate, you can see that now every flit is roughly getting at most or at least 2 hops extra, but deflection rate of D-bar is also increasing. Even at slightly higher load, D-bar packets are experiencing roughly 1.5 deflections per flit. So, this graph tells that when the load is increasing, the conflict is increasing and more packets will get deflected away. But the number of flits deflecting away is drastically reduced in the case of D-bar because of a better priority mechanism. You can see the same trend in the case of transpose traffic where MinBD has heavy deflections, whereas D-bar has a slightly lower number of deflections. So, this shows that by virtue of the priority mechanisms, the changes in the router microarchitecture are able to reduce the number of deflections, thereby reducing the average packet latency. So, the whole concept of moving towards bufferless deflection routing, which was mentioned in the chipper, was to reduce the area as well as power consumption, because we are getting rid of buffers. But once we do not have buffers at higher traffic rate, it will lead to heavy deflections. And that was being mitigated by introducing the concept of side buffers, first proposed by Chris Fallin and et al. In the Knox paper, leading to the MinBD design. And some of the microarchitectural features proposed by MinBD was been revisited by the authors of the D-bar paper, and they were trying to put up a different kind of a priority mechanism, trying to get rid of the dual ejection ports and some kind of a dual injection unit where fairness is given to both packets in side buffer as well as in the core buffer. So, that is going to be the performance analysis. Now, coming to the hardware overhead. So, once you have a design in hand, computer architects normally try to describe this hardware in hardware description language like VHDL and Verilog. So, once you model your microarchitectural feature using this hardware description language, then we are going to synthesize them using the appropriate IDE tools and find out the synthesis report in terms of area and power consumption. So, both MinBD and D-bar routers, while implementing on this Verilog design, it was shown that the stage 1 of D-bar is 17% less time consuming than that of stage 1 of MinBD. Because in MinBD you have dual ejection unit, you have a redirection, you have a buffer inject. So, there were many units on stage 1 of MinBD, but when compared to that, the number of combinational block needed in implementing stage 1 of D-bar is rather less, which is, so the maximum propagation delay for the circuits for D-bar is 17% less when compared to that of MinBD. But the overall latency of stage 2 is same. So, because stage 2 is more or less same, you have a silver fleet, you have a permutation deflection network and buffer eject. Here also you have a routing mechanism that takes care of the priority plus PDN plus buffer eject. So, stage 2 is basically same. Since both MinBD and D-bar are pipelined routers, we know that in the case of a pipeline of multiple stages, whichever stage is taking more time, and that is going to govern your pipeline timing. So, since even though we save little bit in D-bar in the stage 1, since stage 2 both for D-bar and MinBD it is same, then that means that since stage 2 dominates over stage 1 in latency, D-bar can operate in the same frequency as that of MinBD. So, D-bar routers will also operate at the same frequency. So, the critical path of D-bar is same as that of critical path of MinBD. Since the dual ejection bandwidth is being reduced, we could achieve 18% of reduction in channel wiring due to the single ejection port. So, these are the performance that we gain with respect to the D-bar routers in comparison with MinBD. Now, let us try to understand what are the problems associated with D-bar router. So, we have to see the sequence. The concept of chipper router itself was evolved from the limitations of BLUS, the conventional BLUS router, and the limitations of chipper was addressed by MinBD router. Limitations of MinBD router was addressed by D-bar router. Now, we will try to see what are the limitations of this D-bar router. So, the first problem with respect to D-bar is channel wastage. This is the router pipeline of D-bar. Now, consider the case that you have a flit that is waiting in the core buffer, and injection from core buffer into the router pipeline can happen only if one of the link in the router pipeline is idle. So, when there was a flit that is waiting to enter into the router pipeline, it was denied permission due to the fact that all the channels were having valid flits. But it so happened that after the port allocation stage, one of the flit got a non-productive port and that flit was moved out from the side buffer, essentially leading to one of the output port going idle. This scenario is called channel wastage. So, I will rephrase the same scenario. We have a flit that is waiting in the core buffer to enter into the router pipeline. At that time, entry into the router pipeline was denied because none of the internal flit channel was idle. So, the flit will wait there. But it so happened that all the flits that was there in the internal pipeline channel, after the port allocation, some of the flits got non-productive port, and we see that the buffer eject unit that is going to remove the flit has found that one flit is been removed. For example, you assume that was a flit that was assigned with east output port. So, the flit that got east output port was not happy. So, that flit was being taken to the side buffer because it is a deflected flit. Now, you have a scenario, your east port is idle, but we have a flit in the core buffer that is looking for east output port. So, to summarize, a flit looking for a specific output port is waiting in the core buffer because it cannot inject. At the point of injection, all the channels were busy, but that specific output port for which the flit is waiting, that particular port is idle. This is called channel waste because we are wasting a channel when there is a valid flit looking for the same channel. This roughly happens around 18% of cases when we implement the D-bar router. The second one is called problem of internal movement of flits. So, consider the case that you have a flit that is entering from core buffer that is going into the dual injection unit and it goes all the way into the permutation deflection network. It so happened that the flit that got recently added, the flit is going to have, in going into the permutation deflection network, it got a non-productive port. Once you get a non-productive port, the buffer eject unit is going to take you into the side buffer. So, it so happened that in 11% of cases, a flit that recently entered from the core buffer reached in the permutation deflection network, got a non-productive port leading to movement into the side buffer. So, essentially it is a movement from core buffer to side buffer. This is called problem of internal movement of flits. There is no productive movement for the flit is just moving from one array inside a router to some other array inside the same router. So, this is called core buffer to side buffer movement. It happens roughly around 11% of cases. The third limitation of D-bar is problem of internal flit movement from side buffer to side buffer. So, the concept of side buffer to side buffer is there was a flit which reached side buffer because it was assigned a non-productive port in the previous cycle. So, we have a flit in side buffer which tries to re-enter the router pipeline, and in this cycle also, upon reaching permutation deflection network, it got again a non-productive port. So, that flit is going back to side buffer again. This happened in 22% of the cases. So, a flit which was there in side buffer, enter the router, go for port allocation, again come back to side buffer because the port allocation was not in favorable for the flit. Why this is happening? When a flit is re-injecting into the router pipeline, its priority is not changing because in D-bar, the priority is based on hops to destination. Since the priority is still the same, the flit may again compete with the other flits, it may not get the productive port. So, here also we have side buffer to side buffer issue. So, if you look at the problem of channel wastage, the problem of internal movement of flits, and there is one more problem that is called older flit penalization. In D-bar, the priority mechanism used was oldest like hops to destination. So, when you have a really old flit, he is not even nearer to the destination, those flits may lose out in arbitration to a newly generated flit. So, consider the case that you have a newly generated flit travelling to a nearby destination, you have an old flit that has travelled all the way, but still it has to go further, and these two when they compete, since the priority is not based upon age or round robin, the priority is based on hops to destination, the newly generated flits whose destination is nearby will penalize an old flit. So that is called the problem of older flit penalization. You can see that how much percentage of flits are being affected by problem of channel wastage, problem of internal movement of flits, and problem of older flit penalization. You can see that as injection rate increases, all these problems are going to affect more number of flits. You can see that all these graphs are tilting towards the y-axis. So the limitations of D-bar are more exposed when you go for higher traffic injection rates. So here was yet another proposal by Bhavna Nayak et al. It was published in Conference on Computer Design in 2013. They were proposing a new router called Slider Smart Late Injection Deflection Router, where this is the router pipeline. It is just reorganizing the various units in D-bar itself. So three main features is, there are three units: routing unit, the eject unit, and prioritization unit. So parallelizing independent operations. Then we have a concept of selective preemption. So you have a preemption logic that comes over here. So the PDN will move to stage 1. This is port allocator is basically your PDN. So PDN is moving to stage 1, this stage 1, and the injection happens late in the pipeline. Rather than having an injection unit early, the injection from side buffer as well as core buffer is happening late in the pipeline, and there is no movement from core buffer to side buffer and side buffer back to side buffer. Packets will enter into the inject stage only if they are going to get a productive movement. So the concept of a smart late injection is, inject the packets as late as possible in the pipeline, such that you look into what are the ports that are available, and if your productive port is available, then inject there. So smart late injection deflection router. So this is called the concept of slider. We have three parallel operations that can be done. The routing unit only want the destination address. The prioritization unit by hops to destination priority, that also wants the destination address. So they just extract the destination address field from the incoming flits, and the flit will directly go to the eject stage, and they are going to eject the flit. And then we have the port allocator. So the port allocator is basically your PDN, and the eject unit will take care of the flit to be ejected. And remember, slider comes back to a single ejection bandwidth, and port allocator is normal PDN. After that, since the priority is already computed and stored in the flit, the stage 2 of the router pipeline has the preemption logic. So if the flits in the side buffer and the core buffer are really starving, then preemption happens. If they are not starving, then we have the inject unit, the basically dual inject unit. Based on odd even cycles, either flit will be injected from core buffer or flit will be injected from the side buffer. So the concept of late injection is a bit tricky. So the concept of smart late injection, we will just try to understand what it is. So this is the inject unit. What you see there down is the core buffer, and what you see there up is called the side buffer. So there are two green flits waiting in the side buffer, and there are two flits in the core buffer. The blue flit is waiting for west output port. So its productive port is west, and the red flit is looking for the south output port. So consider a scenario that by the time this flits reach the injection stage, the south channel is empty. So the south output port, there is no flit. You have a flit going to north direction, you have a flit going to east direction, and then you have a flit moving to the west direction. The south channel is empty. You can see that in core buffer, you have the red flit waiting for south. So this red flit will enter from core buffer, and then it is going to travel. So the flit got its productive port. That is what the takeaway is. So this is called a restricted injection. Restricted injection means a flit will be injected into the router only if the direction which takes the flit in a productive way, which takes the flit closer to destination, or the productive port is available for the flit. In this case, we have seen that the red flit is looking for south output port, and exactly south output port is empty. So flit will be injected into the router only if the productive port is idle. Now consider another scenario. We have two flits, one is waiting for west, other one is waiting for north, are there in the core buffer, but only the south channel is empty. The flit, already the north output port has a flit and the west output port has a flit. but there is an empty south channel. Since it is restricted injection, the fluid won't get injected into this particular empty slot. So, there is no fluid that is injected. And then we move to the non-restricted injection. So, if you are very much choosy about injecting a fluid in the case of a slider, then your core buffer and side buffer will get accumulated with fluids. You may not be able to inject fluids because your preferred port may not be freely available. Some other port may be freely available, but since your preferred port is not there, you refrain from injecting the fluids. If this scenario continues for multiple clock cycles, then slowly your core buffer and slide buffer will get accumulated with more number of fluids, leading to overflowing of them or throttling of applications. This is prevented by two modes. You have two different modes for slider. One is called restricted injection, the other one is called non-restricted injection. In the case of restricted injection, fluids will be injected only to their productive output ports. And non-restricted injection, the routers switch into non-restricted injection when the buffer occupancy level of core buffer is more than 50% of its capacity. So, you can see that a core buffer can accommodate maximum of 4 fluids, already 3 fluids are there. So, it is going to be near full. Once it is near full, then there is no point in moving for a restricted injection. You are moving into non-restricted injection. So, in this case, the south is the empty channel, one fluid wants west, one fluid wants west, and the third fluid wants north. But I am not going for restricted injection because now my buffer occupancy is very high. I cannot offer this. So, whatever be the channel that is available, the fluid gets added into it. So, you can see that one of the fluid is added, and that is not the direction that the fluid was looking for. So, the fluid is going to a non-productive port. So, when the buffer occupancy of a core buffer or a side buffer is nearing to full, then the router operates in non-restricted injection. So, fluid will be injected into whatever output port that is freely available. Let us look at the performance characteristics. This is called deflection rate. There is a comparison between 3 deflection routers we learned so far: MinBD, D-bar and slider. MinBD is shown by black color, D-bar is shown by blue color, and slider is shown by the red color. You can see that deflection rate of the slider is much lower than that of MinBD and D-bar. This is because a fluid will deflect in slider only if it is in the non-restricted injection. So, at very low packet injection rate, D-bar has very less deflection rate. This is for transpose traffic and the previous one is for uniform traffic. Once the deflection is low, surely it is going to reflect in the latency also. That is what we can see for uniform as well as transpose traffic in the load versus latency graph. X-axis is packet injection rate, which is an indirect representation of number of packets injected into the network, and Y-axis is the latency. As we can see that D-bar offers a lower packet latency. The red graph is lower to that of blue. Blue is D-bar and slider is the red one. Slider has a lower packet latency than D-bar, and slider saturates. The point of saturation of slider is also late. So, slider can accommodate more traffic. It can manage congestion better than that of D-bar. Similarly, this trend is visible. It has a lower packet latency than that of D-bar. So, the experimental analysis comparison of D-bar and slider. So, if you look at the latency of a single router, this was done by the Verilog implementation. Once we implement all the units of the D-bar pipeline as well as the slider pipeline and then synthesize it, it was found that the router pipeline latency reduction by 25% with respect to D-bar. The slider is the blue one. Slider achieves 25% latency reduction with respect to the D-bar. This latency is not average packet latency, it is known as router pipeline latency. How big or how long is the combinational circuit that implement D-bar? The combinational circuit that implement slider is 25% smaller in terms of critical path length than that of D-bar. Similarly, there is a power reduction of 19% and area reduction of 3.5%. So, D-bar is slightly complex circuit, it is going to consume more power, but slider we are able to cut down the logic significantly less. So, sliders and MinBD more or less the power consumption of the router is same, but when you look at the area, since the combinational logic is being effectively managed, the area you are able to get some close to 3.5%. So, all these new routers for chip multi-core processors, any new idea that if a researcher has, the idea has to be first modeled in a network on chip simulator like BookSim, NogSim, Garnet, many simulators are there. You model them, you get the latency, average deflection rate, many parameters. Similarly, you wanted to know how bulky is the circuit, and that is been done by a hardware implementation, Verilog synthesis of it. So, how will you typically do hardware design verification? You have to write your code, the Verilog code inside some of the ISI tools, and then you synthesize and verify whether all the output signals that you are having is happening in the proper timing cycles. Generate the gate list. So, this is the equivalent gate level circuit of the code that we have, and then you get the synthesis report. How much is the latency, how much is the area, how much is the type, the number of various subunits. So, this is what is known as a synthesis report, and that will tell you what are the hardware components used, and then you generate the bit stream. Once you get the bit stream, you have to program it onto the FPGA, and you can use the FPGA board where the design that you developed inside your computer is transferred into the FPGA board, and the board now models, let's say, your D-bar router or MinBD router or chipper router, and there are pins and knobs that is available. Through these pins and LEDs, you can give some input, maybe a packet number or a destination number, and verify whether they are giving the appropriate results or not. So, today we had a discussion on minimally buffered deflection routers. Basically, it's a side buffer deflection routers. We saw what are the limitations of chipper and came up with MinBD router. The MinBD router was basically focusing on introducing one more level of priority called silver flit mechanism, and then we have a buffer eject unit which will accommodate flits in side buffer. So, the concept of side buffer was introduced first by the MinBD router design, and then you have the dual ejection bandwidth. Now, finding out some of the limitations of MinBD router, the D-bar router was proposed, which has a hybrid ejection unit and as a dual injection unit which will give equal preference to injections from side buffer as well as the core buffer. And the priority structure was totally revamped with a new proposal, like rather than going for golden and silver flip mechanisms, it was better, it was shown that if you go by hopes to destination, that is going to be a better priority mechanism, and the quadrant routing mechanism was also being discussed in the case of D-bar. Now, some of the problems with respect to D-bar was channel wastage and the problem of internal flit movements and the problem of penalizing older flits by the newer flits. And this was addressed by yet another proposal called Slider Smart Late Injection Deflection Router, where the inject unit is kept late in the pipeline and injection happens either in two modes, in restricted mode and non-restricted mode. If it is a restricted mode, packet injection happens only to the productive port. If it is non-restricted happens, packet injection will happen to whatever port that is available. So, in the last two lectures, we are trying to understand, can we get rid of input buffers? Yes, we can. We can remove input buffers, but that has to be compensated by an equally good intelligent system that will take care of the flits. And in order to reduce the number of deflections, side buffers are introduced. Manipulation of data or management of flits to the side buffer and from the side buffer has to be taken care of by appropriate priority mechanisms. So, in this way, we have learned to find out how buffers can be removed, and there are cost-effective replacement for buffers known as minimally buffered or side buffered deflection routers. So, with this we will conclude about the router microarchitecture. So, we have covered what is the basic structure of NOC, the routers, different types of routers, flow control, everything. Over the next few lectures, we will try to see a bigger picture where storages and interconnects are coming together and trying to improve the quality of tiled chip multi-core systems. Thank you.